Okay, so let's see if we can pick up where we've left off. To this point, we've talked about speed being how fast an object is moving, or a little bit more technically, speed being the distance traveled in some period of time. We then went on to distinguish between speed and velocity, velocity also being a fairly common term, but technically velocity is a little bit different than speed in that velocity is speed in a particular direction. You must know the direction an object is moving in order to know its velocity. And because velocity involves both speed and direction, it turns out that the velocity of an object is usually not constant. So the question would be, what three things can you change to change the velocity of an object? Say in your car, what could you do in your car to change the velocity of your car? Well, of course, you could change the speed up or slow down in the car. That would be changing how fast it's moving, which of course is a part of velocity. And you could do that in your car by either hitting the gas or hitting the brake. You could possibly put your foot on the clutch, maybe shift gears. Both those would change the speed, but the two most obvious would be the gas pedal and the brake. So speeding up and slowing down would change speed and again change velocity. The other way you could change velocity in your car would be to change the direction. And of course, to change the direction in your car, you would turn the steering wheel to change the direction the car is moving. And not only could you speed up or slow down or change direction, you could do both. You could be, say, hitting the gas pedal and turning the wheel, which would both cause a change of velocity or two different changes in velocity at the same time, or the brake and turning the wheel. Again, but the point here being that, first of all, velocity and speed are related, but they're different. Velocity involves direction, speed is simply how fast. Now to the next idea here would be, let's move on from there. So the next term we need to talk about is the idea of something called acceleration. And what do we mean by acceleration? Well, typically when people hear the word acceleration, the thing that comes to mind are ideas like getting faster, things getting quicker possibly, or pickup. When you talk about the acceleration of your car, another term that's commonly used is the idea of pickup, or maybe even quickness. Acceleration and quickness are usually terms that you hear associated. And those are okay. They're not necessarily wrong for acceleration, but they're not really good definitions for acceleration. They're not necessarily complete definitions for acceleration. Acceleration, in physics terms, a little bit more technically speaking, acceleration is defined as the change in velocity of an object. Acceleration defined as the change in velocity of an object. If we want to put that, another way to put that would be the rate at which velocity changes. How fast does the velocity change? If you want to put that in terms of an equation, you can begin to develop an equation that would look something like this. We're going to use the letter A over here on the left for acceleration. And as we said, acceleration is change in velocity over some time interval. Or to get the change of velocity, what you would do is take the second velocity, so that would be v2, as you can see there in the next equation, minus v1, what the second velocity was minus what the first velocity was, and then the same thing for the time. What is the time now, or t2, minus what was the time to start with, t1. And you probably remember in science, one of the ways that we can show quantities like v2 minus v1 would be delta v. Delta, the Greek letter delta, it's actually the capital Greek letter delta, looks like a triangle. It's not really a triangle. As you can see, it's slightly different. But that delta refers to change in. It is the abbreviated or the abbreviation in science for change in. So delta v would be change in velocity. And of course, delta t there in the numerator would be change in time. So summarizing all of this, we begin to develop the equation. A, acceleration, is delta v, that's change in velocity, over delta t, change in time. And again, notice the box around that equation, reminding you that's an important equation for us to use, an equation we want to have on our equation page, definitely an equation to have in our notes, and then hopefully sometime in the near future, if not right now, transfer it to your equation page so you have that as one of your essential equations for the year. Acceleration, change in velocity over change in time, the rate at which velocity changes. We can measure acceleration, and anything we can measure has to have units or labels so we know the size of the quantities we are talking about. Well, acceleration is a change in velocity, and as we know from our previous work, velocity is measured in some kind of distance unit over some kind of time unit. For example, meters per second. It's one of the ones we use in the lab. Kilometers per hour, some of the problems we've solved. Anything that measures distance over anything that measures time. An acceleration is velocity over time, or distance unit over time unit over another time unit. The first part there, distance unit over time unit, is our velocity, and we're putting that over another time unit, as you can see from the equation above. And so it's going to be distance over time, or distance over time squared. So for example, meters per second squared would be a unit of velocity, a unit of acceleration. Notice that there's a distance unit over a time unit times a time unit, or time unit squared. Meters per second squared is an acceleration unit we will use a lot throughout the year. You could also have kilometers per hour squared. Notice distance and 2 time units. Those are both great examples of units of acceleration. Distance over time squared. So acceleration, change in velocity over change in time, delta V over delta T. What happens, if we look at that equation, if V2 is less than V1, the initial velocity? What if our velocity now is less than the velocity we started with? Is that acceleration? Is that possible? Yes, it is acceleration, okay? You might say, well, the object is slowing down. It's going not as fast now as it was when we started, so obviously it has lost velocity or slowed down. And it is acceleration. Technically, it's called deceleration, but deceleration is a type of acceleration. It is, if you go back to the original definition, it is a change in velocity. Just so happens it's a negative change in velocity, slowing down, but it is still a change in velocity. And so it is an acceleration called deceleration. Now, just to help clarify this a little bit, my guess, possibly how you've thought about this in the past, maybe up to now, was this, kind of like this graphic here. You thought about acceleration being speeding up, things getting faster. And maybe related to that, but slightly different, you had deceleration that was slowing down. And yes, they were kind of like each other, maybe opposites of each other, but they weren't necessarily the same thing. They were, again, opposites of each other, speeding up, slowing down, acceleration, deceleration. Well, in physics, that's not really a helpful way to think about deceleration. See if this graphic helps maybe explain it a little bit differently. The big overall category we have is acceleration, change in velocity. It's the umbrella category. It's the whole thing. Part of acceleration is speeding up. You can see over there on the left-hand side, getting faster. That's one category of acceleration. What I'm introducing to you now is the idea of slowing down. And slowing down is a change in velocity. Therefore, it is also an acceleration. It fits under the broad category, the umbrella category of acceleration. It just so happens it has its own special name. It's called deceleration. But it's not the opposite of acceleration. It is a special kind of acceleration, all under the big heading, the big category of acceleration. Hopefully that helps you see the distinction. But again, what we're saying here is slowing down is acceleration. It's not the opposite of acceleration. It is a type of acceleration. Again, go back to the definition. Acceleration, change in velocity. Slowing down is a change in velocity. And then, of course, we also have the third mystery category over there on the right-hand side, which we'll get to here in just a couple of minutes. So, here's where we are so far. An object can accelerate by speeding up. Speeding up is a change in velocity. Change in velocity is an acceleration. By definition, that's what we mean by acceleration. An object can also accelerate by slowing down, because slowing down is a change in velocity, And again, change in velocity is defined as acceleration. Are there any other ways, however, that an object can accelerate? Well, let's go back to our definition. Acceleration is change in velocity. Change in velocity involves, if you go back to the very first slide, three things: speeding up, hitting the gas pedal, slowing down, hitting the brake pedal, and then there was a third way that you can change velocity. Go back and look at it. Check your notes. The third way that an object can change velocity is by changing direction, because the definition of velocity is speed in a particular direction. So yes, there are other ways an object can accelerate. An object can accelerate by changing direction. Now, that's probably new. I would imagine even the idea of slowing down being called acceleration is a little bit different, maybe a little bit new for you. And I imagine even more that changing direction being acceleration is new as well. Maybe a different way, or maybe an expansion of the way we've always thought about acceleration. But again, look at the definitions. Acceleration is changing velocity. And if you change your direction, you are changing your velocity. Now, we're not saying here that by changing direction, your speed varies. That could happen. We're not saying that. We're saying if your speed remains constant, even if that is true, if you change the direction, you are accelerating, because if you are changing direction, you're changing your velocity. And if you're changing your velocity, then you're accelerating. Okay, so let's break this down a little bit and let's look at examples. What does it mean to say that an object is accelerating at 2 meters per second squared? What does that mean the object is doing? Well, it means every second that object is going 2 meters per second faster. So maybe at 1 second, it's going 2 meters per second. And if it's accelerating at 2 meters per second squared, in the next second, it's going to gain another 2 meters per second. So after 2 seconds, it would be going 4 meters per second. After 3 seconds, it would be going an additional 2, or 6 meters per second. That's what an acceleration of 2 meters per second squared means. Every second, it's going to gain an additional 2 meters per second. So let's say we have an object. It's initially traveling at 1 meter per second. Its speed is 1 meter per second, and it's going to accelerate at 3 meters per second squared. It's initially going at 1, and it's going to accelerate at 3 meters per second squared. How fast would our object be going when it starts? That's right, it would be going 1 meter per second. Okay? How fast would it be going after 1 second? Well, if it starts at 1 and every second it gains 3, accelerating 3 meters per second squared, then after 1 second it would be going 4 meters per second. How fast would it be going after 2 seconds? Well, it's going to gain an additional 3. So it would now be going 4 plus 3, or 7 meters per second after 2 seconds. How about after 3 seconds? Well, it was going 1, then 4, then 7. So after 3 seconds, it's going to be going an additional 3, or 10 meters per second. Now, how about after 6 seconds? Let you think about that one for a second. And if you just walk that through very carefully, you can just do it second by second. Hopefully you see that after 6 seconds, it should be going 19 meters per second, if I did mine correctly. Every second, it's going to gain an additional 3 meters per second, starting at 1, and then each second after that, picking up an additional 3 meters per second. An acceleration, 3 meters per second squared. Let's talk about this for a second. Is it possible to have an object with a big speed and very little or no acceleration? An object that has a large speed but no acceleration. And hopefully you've had a chance to think about that, or take a second to think about that. Maybe want to pause the video for a minute to think about that. An object that has a big speed and no acceleration or very little acceleration. Well, sure it is. You could have an object that's moving very fast. It's just not getting any faster. So for example, you're riding in your car, you're going 75 kilometers per hour. That's pretty fast, relatively speaking. But you're not getting any faster. You're just staying at 75 kilometers per hour. You're not speeding up or even slowing down. You're just maintaining a constant high speed. So that is definitely possible. Is it possible to have an object that has a big acceleration but very little or no speed? Maybe you want to pause the video and think about that for a second, or ponder that idea. Could you have something that has a large acceleration and maybe very little or no speed? Well, sure it is. You could have an object that's not moving fast, but it is getting faster very quickly. So for example, maybe consider a bullet when you shoot a bullet out of a gun. When the bullet is first shot, it's not moving very fast yet. It's almost at zero, but it is in the process of getting moving very quickly, because after a second, or even after 2 or 3 seconds, now the bullet's going to be going very fast. Or just think about the situation when you drop something. When you first let go of it, it's hardly moving. It's for the first instant, for the first moment, it's not moving at all. It has zero speed, but it is in the process of getting faster. It's speeding up very quickly. It just hasn't been speeding up long enough to get up to some great speed, some even measurable amount of speed. So it is accelerating, it's getting faster, but it just hasn't been doing that for a period of time in which it can actually get up to some great speed. And so yes, it's possible to have big acceleration with very little or even no speed at all. Let's say we have an object moving to the right. Could that object be accelerating to the left? What would that mean if it's accelerating to the left? Well, we alluded to this a little bit the other day, but we said direction, one of the ways we indicate direction is by using negative. And so this would be an object that has a positive velocity but a negative acceleration. Is that possible? Think about that for a minute. Maybe you want to pause the video and consider that. So yes, we can have an object that's moving to the right and accelerating to the left. It simply means it's slowing down. And again, slowing down is acceleration. It's a change in velocity. And so you can have an object moving to the right. Okay, it's moving, but it's slowing down as it's moving. That could be, for example, you in your car. You're hitting the brakes, maybe gently applying the brakes, and so you're still moving. You still have a velocity, but that velocity is decreasing. And so you have a negative acceleration. And so yes, that's definitely possible. Can you have it moving with a positive velocity and a negative acceleration? Yeah, that was the situation we just talked about. Again, positive and negative could be captured, could be denoted by using right and left, okay? Or they really could mean very much the same thing. To give another example, you have an object that you throw upward as you throw as the object is moving up. Okay, it has a positive velocity, but it's slowing down. It's losing velocity as it goes up, of course, because eventually it's going to stop moving at some point. And so it still has a velocity, but the velocity is decreasing. And so it has a positive velocity, but the acceleration is negative. Okay, acceleration is slowing down as it moves up. And so lots of examples of that. That may be the simplest of those. Let's try a couple of example problems here, maybe a couple word problems, and I'll leave this on here for a minute and for you to try it on your own. Possibly try this in your notes. Car accelerates from 25 meters per second to 32 meters per second in 3 seconds. What's the acceleration of the car? So we've got a car. And excuse my handwriting here, but its initial velocity, I'm going to right now call that V1, is 25 meters per second. And again, pardon my bad handwriting here with the mouse, but 25 meters per second. And its final velocity, V2, is 32 meters per second. Kind of laughing at my own writing here. And I forgot an equal sign there, of course, so we'll go back and get that equal sign. And I've got a time here, time equal to 3 seconds. So 3.0 seconds. Hopefully you can actually read that. The equation we're working with here is that acceleration, goodness gracious, that's horrible, is equal to change in velocity over time. And we said change in velocity means v2, and be careful with this, it's always the final value minus the initial, so v2 minus v1 over the time. So we could solve for this acceleration. A, we're going to take the second velocity, which is 32 meters per second. Hopefully you can actually read this chicken scratch there. Minus the 25 meters per second, the initial velocity, over the time of 3 seconds. So 32 minus 25 leaves us with 7, and that's 7 meters per second over, and again, please excuse the atrocious writing, 3 seconds. 7 divided by 3 leaves us with about 2.3. Now let's look at the units here. I'm going to get a different color just to look at the units. Here's what I have. I have meters over seconds. So meters per second, and I'm dividing that by seconds. Now just to make this easier with the compound fraction, I'm going to put a seconds over 1. Okay. And are you familiar with this way to solve complex fractions? You multiply the outside 2, so meters times 1 is just meters, and then multiply the inside 2, seconds times seconds is seconds squared. So what this whole thing becomes with this compound fraction, meters over seconds is meters over seconds. That's supposed to be an S, so let me fix that. Meters over seconds squared. So our units for our final answer for our acceleration, which is what we thought they should be, but they work out that way mathematically, meters per second squared. So this object that goes from 25 to 32 meters per second in 3 seconds has an acceleration of 2.3 meters per second squared. Hopefully that makes sense to you. Hopefully you can read all that chicken scratch writing. How about this car? An object is traveling, this vehicle, traveling at 35 meters per second when its brakes are applied, and it slows to 20 meters per second, an acceleration of negative 7.9 meters per second squared. And the question is, how long did that take? Now, first of all, notice the negative 7.9 meters per second. Why is that negative? That's right, it's negative because the object is slowing down. It went from 35 to 20. It's losing speed, decreasing speed, decelerating, as many of you said. Therefore, it is a negative acceleration. Mathematically, that comes out to be negative. We show that it's slowing down by making it negative. But in any case, let's see if we can figure out how long this takes, the time that it takes for this to happen. And once again, I'll try to solve it here. I will try to write as neatly as I can. Hopefully you're solving this for yourself, but let's see what we have here. So the equation we're working with is this one, that acceleration is change in velocity, that's delta V over t. We're told that we have an acceleration of negative 7.9, goodness gracious, meters per second squared. I really need to get a tablet to do this, but we'll make this work for right now. 7.9 meters per second squared. And going back up here for a minute, what we mean by delta V, remember, is V2, the final velocity, or the second velocity, minus the initial velocity. V2 minus V1 over the time, how long that takes, or the time interval. Now, just as a side note here, we had also written delta T right here this time as delta T, the change in time. It's really a time interval, and so whether we call delta T or T really doesn't matter. It is some amount of time. That's what we're looking for. So we can write either way. It's just some amount of time. Okay, so v2 minus v1, our second velocity minus our first velocity. Well, our second velocity here is 20 meters per second. The car started at 35 and it slows down to 20. So the second velocity, you could also call it the final velocity here, is 20 meters per second. Minus the first velocity, its initial velocity, initial speed, 35 meters per second. Writing's getting worse, but hopefully you can decipher that silliness. Over the time. This is my acceleration, A. This is my initial velocity, my final velocity. This is my initial velocity, V2, V1. So now let's do the math. Let's see if we can clean this up here a little bit. We still have negative 7.9 meters per second squared equals 20 minus 35 is negative 15 meters per second. Got to keep the negative there. And that's part of the reason this is so important we get this order right. It's the second velocity or the final velocity minus the initial over t. And we've got two more steps of algebra to solve this. We can multiply both sides times t. Then we can divide negative 15 by negative 7.9. Multiply both sides times the t, it gets it out of the denominator here and moves it over here. And then to get the t by itself, we're going to divide 15 by 7.9. So we should be able to get this down to t, whoa, that's horrible, that's just a t, sorry, equals, and let me check this on my calculator. And when I do that carefully, I get 1.9 seconds. Wow, that's really bad. Highlight that for you. That is quite atrocious. Hopefully you can make some sense of that. Now notice here that it does work out correctly in terms of the signs. It's a negative 15 divided by a negative 7.9, so I get a positive 1.9. I cannot have a negative time. Time only moves forward. There's no such thing as time moving backwards. And so that's part of the reason here, at least there's no, let me go back to that a second. In Newtonian mechanics, Newtonian physics, there's no time going backwards. We'll talk more about that later. But in any case, times always must be positive, which it is here. Negative divided by negative is positive 1.9 seconds. Let's try one additional problem here. A bicycle starts traveling at 9 meters per second, accelerates 2.1 meters per second squared for 2.7 seconds. We want to know the new speed of our bicycle. So here's what we have here. This value here, this 9 meters per second, is my initial or my V1. I'm just going to pull all these out and label them here to make things simpler in the end. So V1 is 9.1 meters per second. Notice the units there let me know it's a speed, not a velocity, because it's meters over seconds. However, they do give us an acceleration here. It's speeding up. It's changing its speed to 0.1 meters per second squared. Now notice, you remember a second ago I said it's speeding up. How do we know that it's speeding up as opposed to slowing down? Well, it's a positive acceleration, positive 2.1, which means it's gaining speed, not losing. And the last piece of information we have here is the time. They tell us that the time is 2.7 seconds. Pardon me. And we're asked to find the new speed of the bike. That's V2. The second speed of the bike. So we're looking for this. This is what the question is asking me. Going back to my equation, acceleration is change in velocity. We'll write it that way first. Delta V over the time, or delta t, I'm just going to write as time for now, and delta v means v2 minus v1 over the time. So now we can plug in what we know and solve for what we don't. So we're told that the acceleration a, the left-hand side of the equation, is 2.1 meters per second squared. Gosh, I really need to get a tablet to write on these problems in these presentations. But again, hopefully you're making sense of this. A is 2.1 meters per second squared is equal to V2, which is what I'm looking for. Okay? I don't know that value. I don't know how fast it's going after it speeds up. But I do know V1, and that was 9 meters per second. If you're laughing at me, you try this sometime, writing all these out with the mouse. It's not as easy as you may think. And then the time, 2.7 seconds. Now, before we actually jump into the math of this, let's talk about V2. What kind of number do we expect to get for V2? V2 is speeding up. Okay? It started at 9 and it's getting faster. It's accelerating, a positive acceleration. So do we expect V2 to be a number bigger than 9 or less than 9? That's correct. We expect V2 to be a number bigger than 9 because it's getting faster. And so just to check our answer to make sure we're doing it right, that's kind of nice to look at. And so the steps of algebra would go something like this. It would be 2.1 meters per second squared. And I'm going to multiply that times 2.7 from the lower side of the right side of the equation. So that would be 2.7 seconds equals, still have the same numerator, V2 minus 9 meters per second. That's quite atrocious. Apologize for that. Again, hopefully you can make sense of that. So I think I'm ready to go ahead and do the algebra now. I'm going to take 2.1 times 2.7, and then I will add 9 to that. Okay, this minus 9 or negative 9 over here, just actually a minus 9. I'm going to add 9 to both sides. So let's put that in our calculator. When I do that over here, I get about 5.7. So 2.1 times 2.7, I get 5.7. And it's meters over second squared times second. So that comes out to be meters per second. One of the seconds in the denominator cancels. This cancels with one of these. So 5.7 meters per second equals V2 minus 9 meters per second. Last step of algebra here, to get the V2 by itself, I would add 9 to both sides. And then to finish it up, I would add 9 to both sides. So let's check that on my calculator. 9 plus 5.7. Hopefully you probably don't need your calculator for that. Let's finish up this chicken scratch. V2 would be, goodness gracious, come on. That's supposed to be an equal. I don't know what just happened there. V2 equals, and it comes out to be 14.7 meters per second. Our object started at 9. It accelerated, positive acceleration, sped up for 2.7 seconds, and it sped up to 14 meters per second. Okay, so for a little bit of practice, I'd like you to read Chapter 2, Section 4. It is the section in your book on acceleration, the material we just talked about. And then there's some questions, actually problems for you to solve, starting there on page 25. You can, you do not need to write the problem. You can write your answer and show your work, enough work so we can see what you're doing. Those will be due next class, at the beginning of class. So again, read Chapter 2, Section 4, and then those problems listed there. See you soon. Have a great evening.